Welcome to the deep dive, where we plunge into fascinating topics and really try to extract the absolute gold nuggets of insight.
That's the plan.
Today, we're tackling a field that's truly, transforming how machines understand and interact with our world. Deep
And
learning.
it really is everywhere now, isn't it?
It feels like it. And we're diving into a great source, Introduction to Deep Learning from Geese for Geeks, to really get a handle on what it is, how it works, and, well, why it's so incredibly important right now.
Yeah, absolutely. Our mission today, I think, is to distill those core concepts, maybe clear up some common misconceptions people have,
Mhm.
and just provide you with a clear, concise picture of this powerful tech. We want to help you gain that knowledge quickly, but, thoroughly. Give you those aha
Yeah.
moments without the overwhelm.
Okay, let's unpack this then. Deep learning. It sounds like more than just another tech buzzword, right? What is it, like fundamentally?
It absolutely is more than a buzzword. At its core, deep learning is a specific kind of artificial intelligence. It's not just programmed for tasks. It actually tries to mimic the neural networks of the human brain.
Mix the brain. Yeah.
And this lets computers autonomously uncover really complex patterns and make informed decisions from just vast amounts of unstructured data, think images, sound, raw text, that kind of stuff.
So when we say mimics the human brain, what does that actually unlock? Like, what can machines do with that capability that maybe standard programming couldn't handle? What's happening under the hood?
That's really the crucial part. A neural network is essentially layers of interconnected nodes, or you could call them neurons,
Okay.
and they work together to process input data. In a, let's say, a fully connected deep neural network, data flows in at an input layer.
Right.
Then it passes through multiple hidden layers. And in these hidden layers, each neuron performs these nonlinear transformations on the data it receives.
Nonlinear, meaning not just simple straight calculations.
Exactly. It allows for much more complex relationships to be modeled. And then finally, it reaches the output layer, which generates the model's prediction. And it's this whole layered approach, this depth, that allows the model to learn incredibly intricate and abstract representations of the data. It's not just seeing pixels.
Right.
It's learning concepts like, chairness, or maybe even recognizing emotion in text.
So it's like the information isn't just passed along, it's actively transformed and refined at each step, each layer building up a more sophisticated understanding.
Precisely. That's
Yeah.
a great way to put it. Each layer extracts features at different levels of abstraction, building on what the previous one learned.
That's fascinating. Okay, we've started to get the essence of deep learning, but this often leads to a really common point of confusion.
hmm
A lot of listeners probably hear machine learning and deep learning used almost, well, interchangeably. Can you help us really pin down the difference? Where does one end and the other become, essential?
Yeah, that's a super important distinction to make. And you're right, they are related. Both are subsets of artificial intelligence.
Okay.
But the key differences are really in their approach and the kinds of problems they're best suited for. Machine learning, or ML, typically applies statistical algorithms to learn patterns.
Right, more traditional stats-based stuff.
Kind of. Whereas deep learning, like we just talked about, uses those multi-layered artificial neural network architectures. That's a fundamental difference.
Okay, so approach is one thing. What else?
Well, data volume is another big one. ML can often work quite well on smaller data sets. Deep learning, though, it really thrives on and often requires much larger volumes of data to show its power.
Ah, so it needs a lot to learn from.
A lot. And then there's task complexity. Traditional ML is often great for problems where the features are kind of well-defined, maybe already labeled.
Mm-hmm.
But deep learning excels at the really complex, often unstructured tasks, like analyzing images, understanding natural language, processing video.
Things that are messy, basically.
Exactly. Messy, high-dimensional data. This also affects training time. ML usually trains much faster. Deep learning models, especially with huge data sets or complex sequences, can take, well, days or even months to train.
Wow,
For
months.
some really big models, yes. And maybe one of the most significant differences is feature extraction.
Okay.
With traditional ML, you often need a human expert to figure out and manually extract the relevant features from the data first.
Right, like telling it what parts of an image to look at.
Precisely. Deep learning, on the other hand, automatically learns these features directly from the raw data. It's an end-to-end learning process. That's a huge advantage.
That saves a lot of work, I imagine.
It does. But there's a trade-off: interpretability. ML models are generally simpler, so it's often easier to understand why they made a certain prediction.
You can see the logic.
More easily, yes.
Mm-hmm.
DL models, because they're so complex with all those layers, often act like a black box. It can be really hard to interpret their reasoning.
Ah, the black box problem. We hear about that a lot. Mm-hmm. And finally, computing power. ML can often run fine on a standard CPU. Deep learning, however, really demands high-performance computers, usually with GPUs, sometimes even specialized hardware like TPUs.
So, quite the resource hog.
Yeah.
Given all these differences,
Okay.
it sounds like picking between traditional ML and deep learning isn't always just about getting the absolute highest accuracy.
Not at all.
Are there times when, maybe counterintuitively, sticking with traditional ML might actually be the smarter or more practical move, even if you have lots of data?
Oh, absolutely.
Yeah.
For sure.
Okay.
If you have simpler problems, maybe smaller scale stuff, or if your data set isn't massive,
Right?
or, crucially, if you absolutely need to understand the why behind a decision, think regulatory compliance in finance or certain medical applications.
Where explainability is key.
Exactly. Then traditional machine learning is often the better choice. It's more transparent, often more efficient for those cases. But for those really big, messy, unstructured data sets, images, text, sequences, and where having the model figure out the features itself is a game changer.
That's where deep learning becomes the much more powerful tool, if you have the data and the compute power to back it up.
It's amazing to think about the journey this field has taken, how it evolved from these initial, maybe simpler ideas, hit roadblocks, and then needed these critical breakthroughs to get us where we are now. What were those really early steps, and what were the limitations that kind of forced the next big leap?
Yeah, the history is fascinating. The very first step, really, was back in the 1950s with the perceptron.
The perceptron.
It was just a single-layer neural network.
Yeah.
Super innovative for its time, showing a machine could learn from data at all. But it had this one major fundamental flaw. It could only solve linearly separable problems. Basically, problems where you could draw a single straight line to divide the different categories of data.
So anything more complex than that, it just couldn't handle.
Exactly.
Okay.
It famously failed at the XOR problem, which is a classic example of data that's not linearly separable. You just can't draw one line to solve it. So it kind of hit an early wall. And that limitation, that wall, directly spurred the development of multi-layer perceptrons, or MLPs.
Adding more layers.
Adding hidden layers, yes. And crucially, adding nonlinear activation functions within those neurons. That was a game changer because it allowed the network to start modeling more complex nonlinear relationships in the data.
Okay, so the layers plus the nonlinearity.
That was key. But the biggest leap, the thing that really unlocked the potential of these deeper networks, was the development of backpropagation.
Backpropagation, I've heard that term. What exactly did it enable?
It's basically an algorithm that allows the network to learn efficiently from its errors. It calculates how wrong the output was,
Okay.
and then it propagates that error signal backward through the network, layer by layer, adjusting the connection weights between the neurons to reduce the error next time.
Ah, so it's the mechanism for learning from mistakes in these complex, multi-layered structures.
Precisely. It gave these deeper networks a practical way to train and learn complex internal representations of the data, tackling those nonlinear problems that stumped the simple perceptron. It really laid the groundwork for almost everything that followed.
That makes sense. Quite the turning point. So we've seen the evolution, but today's world of neural networks is incredibly diverse. You described it earlier as a toolkit. It feels like there are all these specialized architectures now. Can you walk us through some of the key players and what specific kinds of challenges they're uniquely designed to tackle?
Certainly. It really is like a specialized toolkit. Starting with perhaps the simplest, we have feed-forward neural networks, FNNs.
Okay.
Here, data just flows in one direction input through any hidden layers to the output. No loops. They're used for more basic tasks, like simple classification where the patterns aren't overly complex or sequential.
Got it. Straightforward flow.
Then you have convolutional neural networks, or CNNs. These are superstars for grid-like data, especially images.
Right. Vision tasks.
Exactly. They use special layers called convolutional layers that act like filters, scanning the image to detect spatial hierarchies like edges first, then shapes, then maybe object parts, and finally whole objects. Indispensable for computer vision.
Makes sense. What about data that happens over time, like language or, say, stock prices?
For that sequential data, we turn to recurrent neural networks, RNNs. These have loops in their connections.
Loops.
Yeah, it allows information to persist, giving the network a kind of memory of previous inputs in the sequence. This is crucial for tasks like language modeling, predicting the next word, or speech recognition.
So they remember context.
They try to. Basic RNNs had some trouble remembering things over long sequences, which led to variants like LSTMs, long short-term memory networks, and GRUs, gated recurrent units.
Okay.
These have more complex internal mechanisms, sort of like gates, that help them learn which information to keep and which to forget over longer periods. They're much better at handling long-term dependencies and sequences.
Interesting. What else is in the toolkit?
Well, then you have generative adversarial networks, GANs, which are really fascinating.
GANs, right, creating realistic images.
Exactly. They actually consist of two competing networks. A generator tries to create realistic data, say images of faces, and a discriminator tries to tell the difference between the generator's fake data and real data.
So they battle it out.
They do. And through this competition, the generator gets incredibly good at creating highly realistic outputs. They're used for image generation, style transfer, data augmentation, lots of creative stuff.
Cool.
We also have autoencoders. These are generally unsupervised networks, meaning they don't necessarily need labeled data. Their goal is to learn efficient encodings of data.
Encodings, like compressing it.
Sort of. They compress the input into a smaller latent representation, it's kind of summary, and then try to reconstruct the original input from that summary. This makes them really useful for dimensionality reduction, finding anomalies, or even removing noise from data.
I see. And you mentioned one more that's been huge lately.
Yes, transformer networks. These have absolutely revolutionized natural language processing, NLP, and are now finding uses elsewhere too.
What's their secret sauce?
Their core innovation is something called the self-attention mechanism. It allows the network to weigh the importance of different words or parts of the input data relative to each other, regardless of how far apart they are in the sequence.
So it knows which words are most relevant to understand another word, even if they're far apart.
Precisely. This overcomes some limitations of RNSLSTMs with very long sequences. Transformers excel at tasks like machine translation, text generation, question answering, sentiment analysis. They power many of the big models you hear about, like GPT and BERT.
Wow. It really does sound like each network type has its own kind of superpower designed for very specific challenges. But is there ever a case where, the lines blur? Or where someone might try to use one type for a task usually handled by another, maybe with weird results?
That's a great question. And yes, while each has its clear strengths, researchers are always experimenting, pushing boundaries. You could theoretically try to use a basic feed-forward network for image classification.
But it wouldn't work well.
It would likely be far less efficient and much less accurate than a CNN, which is specifically built to understand spatial patterns. Similarly, using a very basic RNN for, say, translating a long document would probably struggle with context that a transformer handles much more elegantly due to attention.
So you can try, but you're often fighting against the architecture's design.
Pretty much. You usually sacrifice performance, efficiency, or both when you use a tool that's not optimized for the job at hand. Sticking to the right architecture for the problem is generally key.
Okay, this is where it gets really exciting for me, seeing where the rubber meets the road. Where does all this theory and these architectures actually, change things in the real world? How is deep learning transforming industries and maybe even our everyday lives?
Precisely. This isn't just academic anymore. It has incredibly tangible impacts. Let's take computer vision. Deep learning powers the object detection and recognition in self-driving cars.
Allowing them to see.
Exactly. To see pedestrians, other cars, traffic lights. It's also used heavily in surveillance systems for quality control on manufacturing lines, and it enables much more sophisticated robotics. In medicine, it's achieving remarkable results in image classification for medical scans, helping doctors spot tumors or other anomalies, sometimes even better than the human eye. And image segmentation helps identify very specific features within complex images.
Incredible. What about language? You mentioned NLP.
Huge impact there, too. Deep learning models are behind automatic text generation, like writing summaries, maybe even drafting emails or articles.
Right, like some of the AI writers out there.
Exactly. They also enable much better language translation, breaking down communication barriers. Sentiment analysis helps businesses understand customer feedback at scale by gauging the emotional tone of reviews or social media posts. And of course, speech recognition, powering the voice assistants on our phones and smart speakers, converting speech to text. That's all driven by deep learning.
Yeah, that's become so common now.
And one more area, reinforcement learning. This is where deep learning agents learn by trial and error, maximizing rewards in an environment.
Like game playing.
Famously so.
Yeah.
Models have learned to beat world champions at incredibly complex games like Go, chess, even complex video games like StarCraft or Dota 2, often by discovering strategies humans had never thought of.
Just by playing itself over and over.
Millions or even billions of times, yes.
Yeah.
Beyond games, it's used to train robots for complex tasks like grasping objects or navigating tricky terrain, and even in optimizing control systems for things like power grids, traffic flow, or complex supply chains.
It's truly mind-boggling to think a machine learned Go, a game of such intuition just by playing itself. It really highlights that ability to find novel solutions. So with all these incredible applications, what are the fundamental advantages? What makes deep learning not just useful, but genuinely transformative compared to older methods?
I think the number one advantage is its potential for extremely high accuracy,
Just better results.
often significantly better, sometimes reaching or exceeding human performance on specific tasks. This is largely because of its ability to learn those really subtle, complex, multi-layered patterns in data that might be missed by simpler models or even human analysis.
Right.
And this isn't just a small improvement. In fields like medical diagnosis or fraud detection, that extra accuracy can have massive real-world consequences.
Makes sense. What else?
The automated feature engineering we talked about earlier is a huge one.
Wait, not needing humans to pick the features.
Exactly. The model learns the most relevant features directly from the raw data. This saves enormous amounts of expert time and effort. But more importantly, it allows the model to potentially discover patterns that a human might never even conceive of looking for.
That's powerful.
Very. Then there's scalability. Deep learning models are designed to handle and benefit from truly massive data sets. The more data, often the better they perform. They also offer incredible flexibility, being applicable across a wide range of tasks and data types, images, text, audio, time series. And finally, they have the potential for continual improvement. As more data becomes available, you can often retrain or fine-tune the models, and they tend to get better and better over time.
That automated feature engineering point where it might find patterns beyond human intuition, that really strikes me as potentially revolutionary. But, okay, no technology is perfect. As powerful as deep learning is, there have to be downsides, right? Hurdles. What are the significant challenges or limitations we still need to grapple with when we try to use these models?
Oh, absolutely. It's definitely not a magic bullet, and there are significant challenges. A major one is simply data availability.
Needing all that data we mentioned.
Exactly. These models are data hungry. They need very large amounts of high quality, often labeled data to learn effectively. Gathering and preparing that data can be a massive bottleneck and expense.
Okay, so data is hurdle one.
Hurdle two is computational resources. Training these large models is incredibly computationally expensive. It often requires specialized, powerful hardware like GPUs or even TPUs.
Which are cheap.
Not at all. And running them for inference, for making predictions, can also be resource intensive. This ties into the third challenge. Training can be extremely time-consuming.
The days or months you mentioned.
Precisely. Especially for very large models or complex sequential data. That iteration cycle can be very slow.
Right.
Then there's the interpretability issue, the black box problem we touched on.
I know why it decided what it decided.
Very hard, often. Because of the millions or billions of parameters and complex interactions inside, tracing a specific decision back to its inputs in a human understandable way is really difficult. For high-stakes applications like loan approvals or medical diagnoses, that lack of transparency can be a serious barrier to trust and adoption.
Yeah, I can see that being a major issue.
And finally, there's the ever-present risk of overfitting.
Overfitting.
This is where the model learns the training data too well, including its noise and quirks. It becomes too specialized to the data it was trained on.
Ah, so it doesn't generalize.
Exactly. It performs poorly on new, unseen data that it hasn't encountered before. Preventing overfitting requires careful techniques during training. So yes, despite all the incredible advances, these challenges, data, compute, time, interpretability, overfitting, are very real and are active areas of ongoing research.
Wow, okay. We have covered a lot of ground today, seriously, from the fundamental concepts like mimicking the brain with neural networks to the different architectures like CNNs and transformers, really nailing down the difference between deep learning and machine learning.
Right.
And then diving into those incredible real-world applications. And just now, the significant hurdles that still exist. It's been a real deep dive.
It has, and I think it's worth echoing the thought from our source material. As we continue to push the boundaries of computational power and dataset sizes, the potential applications of deep learning are limitless.
Limitless. That's a big word.
It feels appropriate, though, doesn't it? Deep learning really does promise to reshape our future, a future where machines can learn, adapt, and tackle complex problems at a scale and speed that was, well, pretty unimaginable just a short while ago.
It definitely feels that way. And thinking about that scale and speed, it raises a really important question for you, our listener. Where do you see this incredible learning power making the biggest difference in the next few years? What problem do you hope it solves? Something to think about.